Right, so yeah, we're gonna do a little streaming. That's what it says right there. Okay, so but anyway, if you watched the previous live stream, we have to we gotta figure out neural nets, and we're making them as small as possible, because it turns out even very small neural nets are pretty hard to understand mechanistically, right? I mean, we're doing like full mechanistics. Like, we're not doing any, like orthogonal vectors and high dimensions or whatever, because that's probably better. But anyway, like this is yeah. Right. So anyway, this is the function we're trying to that we train this neural net to implement. And it's like a random function, right? And so it's just saying, like, this is like, these are the input vectors, like -1, -1, -1, +1. And, like, it's separating the red inputs from the blue inputs. And it has, like, this hidden layer and this hidden layer, and then the output. So it's like 2 hidden layers, basically. 3 sets of weights. And yeah, we're trying to build up, like, we're trying to build up in our short-term memory as a human, like what the neural net is doing. And I mean, it's kind of, I mean, one problem is that, I mean, like, the function itself is random, like, so it's not even really clear what the function is doing. But anyway, we're just gonna hop into it. We've found that working backwards is better, because one thing that the neural net likes to do is it likes to map different points onto the same point. So, like, it reduces the number of points that it has to deal with, which makes it easier to find solutions, but it also makes it easier to interpret. So, hats off to neural nets for making later layers more interpretable. Okay, so anyway, like, this is the last layer here, and it's mapping to a single output. And yeah, so, like, this mapping is being accomplished with a single weight vector and a bias, Also, we're using 10H hyperbolic tangent. I don't know what that is, actually. It's like calculus something. It's a sigmoid, is what, for our purposes. Right, so anyway, so we can see here that the red rows, which, like, are the inputs that receive a +1, the previous layers have mapped the red rows onto 2 points, modulo this guy, but it's the same sign pattern, it's just different magnitudes, so we'll just say it's 2 points. And then everything else, all the blue rows, are mapped onto, like, 1, 2, kind of like 3. I mean, if you count these as zeros, which they're not, but if you did, then it's 3. So like the final layer just has to put a hyperplane between these 2 points and these 3 points, which is easier. That's a dinosaur, if you're curious about that. 2 points versus 3 points, and that's easier to do, because that's only 5 points. That's easier to do than like trying to fit hyperplanes when you have like 16 active points, as you do in 4 dimensions. Okay, so, but also there's like a logic to what the weight vector is doing, which oh yeah. So the logic is, if you look at the 2 middle columns here, like they actually are the target function, except for this one row. I mean, they're equal to the negation of the target function, which, like it's easy to negate, right? Because you just do negatives. So the neural net has effectively computed the function at the penultimate layer, modulo this one error, but the so the final output weight vector corrects that one row, and it does it by, I mean, we can kind of intuit how it might do it, which is that because like it's the error row is the only row that has blue and blue on the outer columns. I guess by this labeling columns 0 and 3, although it doesn't. Yeah, like you would think it would be easy to just have matplot. Anyway, I'm not. It's fine. So anyway, right. So if you have those 2 outer columns that are both blue, you want that to be red, because that's just like you want the output to be red. So you make those 2 weights, like really blue, like really negative, and then it'll and they'll override like the weights, the computation on the inner 2 columns. And then on every other input, the 2 outer column weights, or whatever, the 2 outer columns cancel each other. Kind of modulo these guys, but these are kind of like close to 0. So it still works, I guess. It's not entirely clear why the neural net did that on those 3 rows. I don't know if it had to do it, or because of like linear, like geometric constraints or something, or just left them because it didn't matter. But anyway, so the 2 outer weights are gonna be like large magnitude and negative, because we want to make this guy a red. And then for every other row, we can just use the inner 2 columns, the negation of the inner 2 columns, and you just have to make their magnitudes like smaller than the sum of the 2 outer columns. So it's like an overriding. It's like a conditional override. Is I think like the general logic, but that appears to be the mechanism I keep kind of like. I mean it's not. I mean, you can do multiple interpretations, but anyway, that it's kind of like the general logic there, right? And if we look at the actual weights for this layer, which is us, that's what it's doing. You have like these two large magnitude weights, which look for that one error row, and they overrule on that one row, and on every other row they cancel out, and the middle two guys negate the columns, and that produces the function. Great. Right, so I mean that, I think that's a pretty good mechanistic interpretation of that one layer, you know. So then we have to go back to, you know, understand how we got to this one, you know, to that one, like, mechanism for the output. I mean, also, it's like, you know, like, there's multiple ways to implement this one function, so we're not claiming this is, like, the only solution, nor the only interpretation. But anyway, okay, so we're now going to try to look at layer 3. Okay, so layer 3, these are the inputs to layer 3. These are the outputs, and like the way I have the visualization is that, you know, these this and this are the same, you know, like these are the outputs of layer 3, which become the inputs to layer 4, and they're sorted differently because I think they're sorted according to, yeah, according to the outputs. Like, they're agglomeratively clustered, which means it's this algorithm where you go through all pairs, you pick the closest pair, you join them, that becomes like a new pair, and then you repeat, and it's O(n) cubed. So, and I have like 2 power n points, so I'm running O to power 3n. I actually don't know how exponents work. I think it just multiplies, right? Yeah. Anyway, right, so like this is coming from these are the inputs from the first, or the outputs from the first layer, which we will get to, but yeah, I forgot how to analyze this layer. Like, yeah. Well, I mean, we can see that what it's doing, I mean, basically the thing that it's doing, like, you know, again, like, because you have to keep in mind the mechanism of the next layer. So, you know, it has to maintain that, like, this row, which turns out to be like the error row, right? Like, this row is not like the other red rows for whatever reason. It's you know, I guess like due to the geometry, or who knows, it's treating this row separately from the other red rows. So anyway, because of the mechanism here, you know, you have to have the 2 blue guys. You have to have the 2 blue outer columns. And then the other thing that we relied on is that the two middle columns, like, are the function, like, are the target function modulo negation. And of course, I mean, like, each of these columns is being produced by a single weight array and bias from the previous, rows. So it's kind of like we kind of want to, like, intuit, yeah, like, the mechanism for each of the 4 rows, but then also, yeah, I mean, I think that makes sense, right? Because you're just saying, right, you're just saying, like, we know the output mechanism. It's like the middle 2 columns with, like, an override on this guy. So we have to transform all of these activations to conform to that mechanism. Ditto. It's like, yeah, it has to conform. Like, it's fascist, basically. Like, neural nets are, they're pretty fascist, actually. Right, okay, so anyway, let's see if we can, let's talk about the middle 2 columns. Because first of all, they're mostly the same to each other. And yeah, okay, so alright, so this is what we're asking. We're saying, like, I want to create this middle column using these columns and a weight array of my choosing and a bias, and yeah, and basically I'm concerned with, like, matching the sign pattern. So yeah, I mean, basically this is solving a system of linear inequalities by eyeball. And that's just how we do it. Like most people would say you shouldn't try to solve linear program anyway, but I think the thing is, I mean, I looked at it yesterday and I forgot, but I've forgotten what is happening. I think it's, like, if you look at this column, it's pretty similar kind of to this column. Modulo negation, of course. I mean, like, so in other words, like, if you take this column, which is an input, or like an activate, it's the previous layer activation, and you negate it, then you're going to be, like, just from a sign perspective, right, these are all going to be blue, which is what these are, so that's correct. These are all going to be red, which is what these are, so that's correct. So you're actually going to be incorrect on just 2 rows. So basically, if you can figure out how to error correct on those 2 rows, then you're good. Because you can just set the weights to be, like, high magnitude negative weight on this column with an override on these two rows. And yeah. So then it's kind of like, what do these two rows, you know, how can you distinguish these two rows? BRB. I'll BRB.